your classmates slacker. Okay. Yesterday, I worked with Hannah, and in our 18 tests, we got all of them correct.
Really? What?
I was pretty surprised.
Oh, just you two, or just like all of us?
Hannah.
Oh, yeah.
Hannah and I were partners. Because the tests are sometimes hard to determine, right?
Mm-hmm. Very.
And I say in our 18 tests, we did the wrong test. We didn't follow our, and it's my fault. I'm the one who misread our flow chart. We didn't follow our flow chart on one. It was soluble. We did the next test for insolubility, and that one didn't come out right. Well, I mean, it came out. We did the next one. It was said, and then it was like, it can't be that. That doesn't exist. So we did make some mistakes along the way, but we corrected them all on our own. And then when Nathan graded it, well, Nathan being Nathan, and that one is not wrong. And anyway, but it was kind of challenging, wasn't it? Especially yes. After you had done your assertion, we gave the result of the solubility because it's really hard to tell. But that's part of what they call assaying materials, determining what it contains. Now we're going to talk about mixtures and things like that today. And so a lot of what we're going to see today is very relevant for the lab we just did. So you can take what we did in lab and now say, yeah, now I understand better. So we've already learned what a pure substance is. A pure substance has only one type of, we've learned what an element and a compound is. Now we have a pure substance. So it's not using element or compound here, but substance. And it has only one type of element or one type of compound. So just to recall, difference between an element and a compound.
Element only has one type of atom. Compound has at least two.
Okay, so a pure substance could be a pure compound. So we can have pure water, for instance. H2O is a compound. A mixture is two or more substances. So two or more pure substances, we have the definition of substance. If we have two or more pure substances, no longer would we probably say it's pure anymore, right? So two or more substances, then we're going to call it a mixture. And so think of things around you. What would you identify as clearly a mixture? See if you come up with what's on our next slide.
I have a homogeneous mixture.
Okay. He read ahead or is prepared for class or just knows his material. We have heterogeneous and homogeneous. What's the difference in hetero and homo?
Homo's the same.
Homo's the same?
Hetero is different.
Okay. So a heterogeneous mixture is where we have different things that we can tell are different. Homogeneous mixture, it's still a mixture, so it still has more than one substance, but we can't tell, so it all looks the same. So when you look at your milk, it looks like it's all the same. And so that would be a homogeneous mixture. Whereas you look at your pizza toppings, I clearly see the different toppings, that's a heterogeneous mixture. And of course, those are using macroscopic explanations. So this picture here is coffee. Your coffee has water, and then it has sugar, and then has all kinds of other chemicals that are part of what you extract from the coffee bean. And maybe you put some milk creamer in there or something. But if you mix it all up, it's going to be a homogeneous mixture. If you don't mix it up and you see the creamer, then you say, oh, it's heterogeneous because I can see there's the creamer, there's the coffee. Let's just go to this. This is breaking matter down now using more terms that we're learning today. So we've already learned about elements and compounds. And so on the left there, you have pure elements, things like gold. Then you have pure compounds, things like, now notice it says salt, NaCl, salt, table salt is NaCl. Carbon dioxide, CO2. Ammonia, NH3. And then we have mixtures, and it uses the word impure here. That worked well. I guess that was the graphic I can't highlight. So we have mixtures or impure. They have more than one type of pure material. And if it's homogeneous, you can't tell the difference. So air is actually what I was thinking when I asked about a homogeneous mixture around us. We have air. Air is like 79% oxygen and 29% nitrogen. Wait, did I say that right? 79 and 21. 79% nitrogen, because I think I said that wrong. 21% oxygen, with just trace amounts of other elements. But when you look at air, you don't say, oh, there's the nitrogen, there's the oxygen. It's all mixed together and you can't tell the difference. So that's why it's a homogeneous mixture. On the other side, you have heterogeneous mixtures like sand and water. Right? I love going to the beach. I can always differentiate the sand from the water. My teeth do a great job of it. My body separates them quite nicely. My eyes, not so much anymore because, old people. Oil and water are what we say immiscible. They won't mix. And so you put oil and water and you'll see them separate. So that's why it's there as a heterogeneous mixture. Then we have these things called suspensions. Anyone who knows my wife knows that she's a big fan of colloidal silver. Colloidal silver is a suspension. You have silver suspended in water. Milk is a suspension. If you look at it under a microscope, and I think I have a picture of it under a microscope, you have little globules of fat. They're suspended in water. And when you think about it that way, milk doesn't sound as appetizing. But it's a suspension of milk, fats, and water primarily. This says solid proteins because of the other things in there. Blood is a suspension. When I look at the blood, I can't see they're different, so it's homogeneous, right? These suspensions are under the homogeneous category. But it's a suspension because you have one thing suspended in another. And fog, another example. So pictures are much easier to identify. Granite. When you look at the granite, you can see that's a different type of rock than the stuff around it. Here's another type of rock here. So is that homogeneous or heterogeneous? It's heterogeneous because you can tell the difference. Those rocks, each little rock is going to be made of different atoms that are held together as molecules. So what would we call that if it's a bunch of molecules that are the same? Let's assume that those are pure crystals. Then what would we call that? A compound. Okay, snow and the snow globe is kind of goofy. And the pizza I already used as an example. It's a heterogeneous mixture because you can definitely tell. Here's evil stuff. And
yeah.
I hate olives too.
Olives are
amazing. I love olives.
they are not a thing I like. Anybody have any idea what this picture is? Did you know it was white gold from looking at the book, or do you know what white gold looks like?
You can see the words.
Oh, you can see the...
Not really, I
You're
didn't
right,
like
you
the
can.
words, but you had already used white gold as in the previous slide, so I figured that.
So this is white gold is, I believe, gold and palladium. It says in an upcoming slide. Actually said on that slide 2 slides ago, didn't it? So this is a homogeneous mixture.
It doesn't look like silver.
I could not tell you the difference. Clear seawater. Clear seawater is homogeneous. If you can see things in it, then it would have been heterogeneous. That's why they have the defining, if it's clear. And then the air that we talked about. Okay, so I've got to go back just to make sure I was right. Yes, gold and palladium for white gold. Okay, now we have 2 additional words, solution and suspension. Now I've said the word suspension. A suspension is one type of thing that is in another type, but here's something that is more clear, more direct. Different components in different phases. phases, things like solid, liquid, gas. And so in Amy's colloidal silver, the silver is in solid phase and it's suspended in a liquid phase of water. A solution, all components are in the same phase. So, water or liquid and liquid, water and water wouldn't be. But liquid and liquid, for instance, would be a solution. And we're going to spend a lot of time looking at solutions here coming up. Now, is the air in your house homogeneous or heterogeneous? And yeah, you live in LA. When I was in high school, the air in LA was horrible.
I'm sure it hasn't gotten any better.
Oh, it has. It has.
Oh, really?
Yeah, the Environmental Protection Agency is really tightened down, and the air is much better. So notice the things we have here. They're not just trivial. Homogeneous because it is mixed very well. Heterogeneous because of the dust particles it contains. Can you see the dust particles in the air?
Depends on where you live.
It does depend on where you live, I suppose.
Not really.
In my house,
And it also depends on the light.
if the sunlight is shining and I look at the right angle, I can see them.
Yeah.
And so in that case, I would probably lean on the heterogeneous because of the dust particles it contains. Now, if it's the dust particles contained in the air, now the air is a homogeneous mixture. The dust particles contained, what would we call that? A solution or suspension?
Suspension.
A suspension. Why is it a suspension?
Because it's not mixed isn't the right word, but it's not like
Because they're in
all
different
one.
phases.
There are different phases. The dust particles are a solid phase, and the air is in a gaseous phase.
So is ice a heterogeneous?
If you have pure ice with no air bubbles in it, then it would be homogeneous.
Right.
If you have air bubbles, and you can see those air bubbles, then I suppose it would be a suspension, right?
So you can
Because
have,
one's in gas phase and one's in solid phase.
that's what I was thinking.
Okay, and I won't go through the next ones because they were getting a little sillier. Okay, now looking carefully at solutions. A solution will have a major component and a minor component. That is, you have more of one thing than another. So if I put, let's say, a little creamer in the coffee, assuming coffee we're going to consider for our purposes here to be one substance and creamer the other substance, which do you have more of, creamer or coffee?
Well, it depends on.
Yeah, I know, it depends on the
Yeah.
person. Since I don't like coffee, I probably have more creamer, but you should have more coffee if you like coffee. And so coffee, the predominant one, is going to be considered the solvent. And then the minor component, which would be creamer, would be the solute. So the solute is the one that's the minor thing that's dissolved in the solvent, which is the major thing. And when you put them both together, then you call it a solution.
Is something a mixture if you have a vacuum and then you put something in the vacuum?
No, because vacuum is nothing.
So if you have less creamer, it's a solute.
The creamer would be the solute, assuming you have less creamer than you have coffee.
But
Yeah.
If you have more creamer, then the creamer would be the solvent.
Don't let him confuse you. I said the same thing, so he's just parroting what I said. But just remember, the thing that's the minor component is the solute. The thing that's the major component is the solvent. Then we have this funny thing, a saturated solution. You can only dissolve so much solute in any given solvent. If you put too much solute in, it won't dissolve anymore. And you noticed that yesterday, right? You had your salt, you put it in water. Well, which one was the primary component there?
Water.
Water. So what would we call the water then?
The solvent.
The solvent. So we had water as the solvent, and the solute was sodium chloride. But the sodium chloride clearly did not all go into solution. Where we had as much dissolved whole, couldn't hold anymore. And so that's why we had the leftover salt in the bottom. So then it's a saturated solution. Now we see this on a regular basis. We see it on a regular basis when we look at the air. We measure this thing we call the relative humidity. And I should be clear, humidity is how much moisture is in the air. So which one's the solvent, the air or the water?
Air.
The air, because there's a lot more air than water in the air. So the air is the solvent. What does that make the water? The solute. And the air can hold a certain amount of water. It depends on the temperature, by the way. That's an important thing. And so the humidity is how much water is in the air. But notice I said the relative humidity. The relative humidity, which is what you always see, is the ratio of how much moisture is in the air, the humidity, to the saturation humidity. So saturation is when you have as much moisture as you can. And so if the relative humidity is 65%, that means the amount of moisture dissolved in the air is 65% of the saturation amount, the most you can put there. So when it gets to 100% humidity, what does that mean? It means that the air can't hold any more water, so you're likely to have water-formed droplets.
Or if the air cools.
Or if the air cools, because remember I started this by saying air, the amount of water the air can hold depends on temperature. If the air cools, the saturation level drops. And so if you're at 100% humidity and the temperature drops, all of a sudden you're going to have a cloud form, because a cloud is when you suddenly form little drops of water in the air. Instead of having just water molecules, you have drops. And you see the scattering caused by those drops. That's why we call it a fog or a cloud. They're the same thing. It just depends on where it is, usually what we're going to call it. If it's on the ground, we'll call it a fog. If it's up in the sky and not coming down to the ground, we'll call it a cloud. So where I live, we just have fog. Okay, my house in Colorado. So that's the idea of a saturated solution. And in our experience yesterday, we had saturated solutions. And there's a picture coming up that goes very well with our experiment, but I don't want to skip this important idea. There's like 5 slides probably with this. The concentration. The concentration is a measurement of how much solute you have divided by how much solution. Notice it's not solute and solvent. It's solute and solution. So what is the solution again? The total. So the concentration is how much of the minor component divided by the total amount you have present. So if I put a drop of her hand lotion in her, I will not, in her water bottle, the concentration would be how much of the hand lotion divided by the total volume of the hand lotion plus water. But we have to have units. In measurements, we always have to have units. And there's more than one way to measure this. For instance, what kinds of things could you use to... What kinds of measurements could you use to say how much... Oh, let's start with the easy one. How much solution is present? What would you measure that in? Okay. Bryson said milliliters. That's volume. That's how much space it takes up. Okay, what did you say? Okay. Moles. Moles is a word that's coming up like on the next slide. So I'll talk about it when it gets there, but that's absolutely one of the options. What other options can you think of?
Energy. Weight.
Mass is what I was hoping to hear, yeah.
Gravitational energy.
Proportionality, yeah. So those are 3 of the common things you could measure either the solute or the solution in, or both or neither. So there are different units for concentration depending on what you're measuring. So here we have the mole. The mole is a big number. It's very sad. Former chemistry teacher Charles Friedlein died, I don't know, about 5 years ago now, I guess. But when he was teaching his intro to chemistry class, he had little mole things, like I think he had a mole hat or something, like a mole animal, that he would wear to illustrate this idea of the mole. And it is spelled the same, but it actually comes from short for molecule. But a mole is a large number of molecules. It's 6.022 times 10 to the 23rd molecules. So if I have, one carbon atom, it has a mass of 12 atomic mass units. The definition of the mole is based on the definition of the atomic mass unit. So 1 mole of carbon atoms has a mass of 1 gram. So this number is the conversion factor between atomic mass units and grams. But what we need to know is a mole is just a number, and 6.022 times 10 to the 23rd of molecules. So if we have 1 mole, we have 6.022 times 10 to the 23rd molecules. If we have 2 moles, we have twice that. And so here we have some math work. In class or lab? Recently I did, it was in class on Wednesday. I asked you about the mass of a molecule of water versus a molecule of carbon dioxide. Do you remember how we did that?
We added the hydrogen and the oxygen masses together. And we had
based on the proportions. So H2O, we had 2 times the mass of a hydrogen atom plus 1 times the mass of an oxygen atom. And so for water, we ended up with 18 atomic mass units. Now, if I ask you, what's the mass of a mole of water, the answer is a simple answer. Because it was 18 atomic mass units for an atom, for a mole, it's that same number, 18 grams.
So we just put the grams on.
Right, if you have a mole, you would take the mass and atomic mass units for 1 molecule, and that becomes that same number is the mass in grams for a mole of it. Why do we have this number? It's an easy way to deal with real life sizes of things. Because atoms are not a real life size. We don't say, here's 1 atom of oxygen. Right? It's just not a doable thing. But we can have a container and say this container contains this many moles, this many times 10 to the 23rd atoms. By the way, sucrose, C12H22O11. Let's just do that, the mass of sucrose. First, I say, how many carbons are in sucrose? So I'm going to have 12 times, what's the mass for 1 mole of carbon? Okay, it's 12, and since I said mole, what units is it going to be? Grams, right. That's the real key that I want to get out of this. 12 times 12 grams is equal to 144. Excellent. 144 grams of carbon. And then hydrogen. How many hydrogen do I have? 22. And what's the mass of 1 mole of hydrogen? 1 gram. And then we have 11 oxygens. What's the mass of 1 mole of oxygen atoms? 16 grams. And so if we add those up, 6 and 4 and 2 is 2. 7 and 2 and 4 and carry the 1 is 4. 1 and 1 and carry the 1 is 3. So we have 342 grams for 1 mole of sucrose. In terms of mass, what percentage of the mass of sucrose is hydrogen? Other way around, 22 divided by 342. I took the mass of the hydrogen, which we just calculated was 22 grams, divided by the total mass of 342. And so that's the percentage of hydrogen by mass. What if I did percentage of hydrogen by atoms? No, by atoms, we just take these numbers. So it has 22 out of the 45. So just under 50% of the atoms in sugar is hydrogen. But in terms of mass, it's less than 10% mass hydrogen. How is that possible? Because hydrogen has what? Has a really small mass. And so we have the same type of things. When we talk about our universe is about 75% hydrogen by mass. By number, it's about 91% hydrogen. So you have to understand the differences there when you're doing astronomy. Otherwise, you get really confused because you see both numbers. You need to know, measuring different way. So that's the same type of idea as concentration, different types of units. So 1 mole of sucrose is 342 grams. And so this is just saying 342 grams per mole. It's the calculation we just did. Now, if I were to put 342 grams, 1 mole of sugar in a liter of water, then I have a concentration that I could write as, and we could do it in easy way, 1 mole per liter, or I could say it's 342 grams per liter. Both of those would be correct, but they're different units. So when you measure the concentration, the units is an important thing because obviously the numbers, 342 is not quite the same as 1. So the units are a really important thing in all of science. Now, here's a question just to make sure we've got these ideas squared away. Water has a formula mass of 18. 18 what? Grams per mole, or 18 atomic mass units per atom. How many moles of water are there in 9 grams of water? We back the bus up one step. What's the mass of 1 mole of water? 18 for 1 mole. So how many moles do I have if I have 9? I have half as many, so I have a half mole. Because my mass is equal to the number of moles, which I'll put N here, multiplied by the mass per mole. So I had mass per mole was 18 grams per mole. The abbreviation for mole is MOL, because that E apparently gets in the way. And so that's the mathematical equation we had. 9 grams is equal to N, the variable we're looking for, times 18 grams per mole. With this kind of math equation, how do I get N by itself? Divide by both sides by 18 grams per mole. And so, yes, as Hosanna said, the 18 grams per mole are going to cancel here. On this side, the grams and grams are going to cancel. 9 over 18 is 1/2, or 0.5. And if I look at those units, it's 1 over 1 over moles. But 1 over 1 over you do the, remember, invert and multiply rule. Molarity is the only actual unit of concentration that we're going to pay special attention to. So this is a unit of concentration, molarity. Other terms that are used, normality. Well, that's the one that I remember using a lot of. But molarity is the one that we're going to use here. And the molarity is the number of moles, hence the mole part of molarity, per liter. So when we look back here at the sugar in water, this here, 1 mole per liter, is the molarity. And now this one here is actually, I think it's a little bit, if it's in water, it's correct. Because 1 part of solution per 1,000,000 parts of solution is the technical, or 1 part solute per 1,000,000 parts of solution is the technical definition of part per million. And then it says 1 milligram of solute per 1 liter of solution. Well, a liter of water has a mass of 1 kilogram. And so this is 1 milligram per 1 kilogram is 1 in 1,000,000 grams. But if it isn't water, it doesn't come out to be that 1 in 1,000,000. But you will see parts per million, and this here is the thing that I always remember. That means 1 part per 1,000,000 parts. It makes a lot of sense. And you also will see ppb. What would ppb mean? Part per billion. How big is a billion? A lot. She's technically correct. A billion has another set of 3. And do remember, it's solute over solution, not solute over solvent. Although if you're talking about parts per billion, the number of parts solute is really small compared to the parts solvent. And so it's probably not going to make any noticeable difference, but technically it's solute per solution. Now this graph is something that should resonate with you from yesterday. One of the tests you did, if something was soluble in water, one of the tests you did was to heat it up. And for most things, what's happening to the solubility, that is how many grams of solute in 100 milliliters of water you have at saturation. What happens to the solubility as you heat it up? It goes up. But what's the obvious exception here? Sodium chloride. Now, potassium chloride is only a small increase compared to the others. But sodium chloride, it stays virtually the same solubility. And so that's why that was our test specifically for salt. Salt isn't going to dissolve more if you heat it up. Whereas most things, you see, like, take the sodium nitrate, NaNO3 is an extreme example, going from 0 Celsius to 100 Celsius, it goes from under 80 to over 160. So you're going to have twice as much dissolve. That's a very noticeable difference. So that's why we did that test, because the solubility depends on temperature. Precipitate. We had one test that was looking for precipitate. We put a chemical in, and it precipitated, which we all know precipitation is rain falling, right? Well, that's what usually happens when you have a precipitate. Now, in our example here, this is saying let's take sodium nitrate and let's cool it down. Actually, yeah, let's cool it down. Cool it from 100 degrees Celsius to 20 degrees Celsius. It's in water, so we basically go from boiling water to room temperature water. And the amount of sodium nitrate that the water can hold drops by almost a factor of 2. And so you're going to have sodium nitrate precipitate, which means it's going to be like it's raining in here. And you're going to form little crystals of sodium nitrate down here in the bottom. In graduate school, I did some research with sodium nitrate, and I had to make sodium nitrate crystals by doing this. And so, well, I did it a little differently. This wouldn't make very big crystals, and I wanted bigger crystals, so I did a little different. But I made sodium nitrate crystals by putting them in solution and letting them crystallize slowly.
So they make rock candy.
I didn't know that, but that makes sense.
We should make rock candy for our next lab.
We should.
The problem is then what do you do with it?
You
You eat it.
You do?
Yes.
You don't eat rock candy?
No.
Can we please
That's
do
so
it?
good.
Yeah, we should do it. You take the sugar water and then you put the string in and then
Yeah.
lick it.
We used to make
You
that.
can analyze it if you want.
I can analyze it.
Mostly eat it.
Most.
Come on. You
I will take this
guys
under
up
advisement. I will
there.
consider this.
The problem
What?
is it takes a while.
Yeah, it does take a while.
You threw animals downstairs.
I was a child.
Yeah,
When I was a
know.
child, I spoke
So why
like a
didn't you make
child.
rock
But
candy?
when I became a
It's
man,
not like it's a
No.
2000.
I will definitely consider this.
Cool.
We might do it on the side while we're doing something else.
It does take a long time to
It would be a
build
good side project because it takes, I think it takes like a week.
A week. Yeah, so we'll just have lab for a week. Bring your sleeping bags.
But you get to eat it.
I'll provide the sugar.
But you get to eat your work, your hard work of making them. So you get an award after.
It's like baking brownies, except for it's much more much more labor intensive and much
Not
less
if you make
payoff.
black bean brownies, they're not labor intensive.
Let's just move on. I don't want to think about black bean brownies. Soaps and detergents. Hannah asked about soaps and detergents. Did you not? No, you didn't. Darn it. You asked about the thing that's after that. No, I was thinking about the water softeners, what you asked about.
Oh.
That comes after this. Soaps and detergents work because of the two of the 4 different intermolecular forces we talked about. So what are from strongest to weakest? Now don't put this on your potential test question. From strongest to weakest, what were the 4 different forces that we saw that act between molecules? Okay, so now, as you might have guessed, you can have an ion-induced dipole as well. That just wasn't one that was listed. But soaps and detergents are made with chains, and one chain is nonpolar. So one side of the chain is going to interact with this type of force. And one end of the chain is polar. So this one here is going to interact with that force. So you make these chains, and the chains are going to self-orient to attach to grime. Grime is not polar. And so this non-polar part is going to attach to grime. What is grime? Dirt, little rocks. Polar, what do you put your soap in that's a polar solvent? Water. Water is a polar solvent. And so the polar end of your soap molecule is going to attach to water. So here's what happens. You have this little piece of dirt in your clothes. And the soap molecules come, and see the soap molecule is this chain that has the nonpolar tail, a chain much like, remember we talked about Teflon? The difference in Teflon and this tail is that Teflon has fluorine and this has hydrogen.
Could you go back to the last slide?
This one? So this side here attaches to grime because the grime is also nonpolar. And this side here, because of its ion, attaches to water. There's an E there, it just didn't fit. So the grime then has a whole bunch of these soap molecules that will attach to it. And one side of soap molecules is attached to water, so it moves with the water. The other sides are attached to the grime, so they lift that grime. You watch in the detergent commercials when they say it lifts it and carries it away. That's how it does it. It surrounds it, and then it's carried away by the water. So that's the whole point of a soap. Now, what's the difference in a soap and a detergent? I would have never known.
Soap cleans, detergent doesn't smell good.
The difference, according to our textbook, is that detergents have a more polar end on them. That's the difference according to our textbook. So they're fundamentally the same thing, but detergents are stronger. And so they're going to do a better job of cleaning, assumedly. So make sure we paid attention to this. Which end of the soap attracts the grime? Actually, okay, that's the force. I asked a different question than what I have written here. You guys answered the question that was written with the answers that were written. What I asked was a good question, though. Which end of that is that? Is that the polar or the nonpolar end? The nonpolar end, yeah. Because I asked a different question that was here. And, of course, there's nothing wrong with you asking the question. The nonpolar end then participates in the induced dipole. So what does the polar end do? It has the dipole attraction to what? To the water, to our water, our solvent. Okay, now the water softener. This is the one Hannah asked about. Not Hosanna, Hannah. This picture grosses me out. I have to admit. This is not crazy teeth, just for the record, because that's what I see. I see something from a freak show here.
His hair.
No.
It's a pipe where the water goes
Calcium.
That's pipe with calcium deposits on it.
So they're calcium like crystals.
Yep.
Whoa.
So if you live somewhere where you have lots of minerals in your water, like, I don't know, Lincoln, Nebraska, you've got lots of calcium and magnesium flowing through that water. And you can tell because when you wash, your soap, well, if you're used to it, your soap washes off. Whereas if it's soft water, it doesn't wash off is the way it feels, right? Right?
I feel like you have it opposite. You have it opposite. If it's soft water, it washes off and you can't tell. But if it's hard water, it washes off. It just takes more work.
I don't know. With hard water, I feel like it leaves my hands really dry and crusty.
Well, my experience is with soft water, my body feels slimy when I take a shower. Like I just can't get the soap off. But it probably is because it's actually come off, and I'm used to it being on there being kind of sticky.
I'm pretty sure it's opposite, but I'm not educated in that field, so.
Well, and I'm talking perception here too. So this is a bad thing. It's a bad thing because it will clog your water pipes, and also it's not very pretty because you have lime deposits on things like your refrigerator. You have a place where it dispenses water, and you have little drips, and over time, you build up crust on it. It's kind of nasty. Or let me take a very practical example. I, of course, like to have a massage shower, a thing that gives me a pulsation. Feels good. And so I bought a shower head, and after about 3 years, it stopped pulsing. Well, the way it pulses is very simple. Inside, it has like a propeller, and the water makes it go around in a circle when the water's on. But it got stuck. Why did it get stuck? Because of lime deposits. Well, about 3 years ago, Amy said, we need to get a water softener. So you know what we did? We got a water softener. Because when the wife says, months after, all of a sudden my shower head started pulsing again.
Next time you can just put vinegar on it and put a bag of vinegar.
That also works. Why does that work? You just learned about that in lab yesterday.
Why don't you at me?
Because you were my lab partner.
I was also not having it yesterday.
We put vinegar as one of our tests, didn't we?
It bubbles.
It bubbles. Why does it bubble?
Because it breaks down.
It breaks down the calcium carbonate. And that's what that rock actually is calcium carbonate. I said calcium, I should say calcium carbonate. And so it breaks down the calcium carbonate, releasing carbon dioxide gas. That's what the bubbles are. And so putting your shower head in a bag filled with vinegar, that vinegar is going to break down the calcium carbonate. Awesome, right? We saw that in action yesterday. So those are bad things. A way to get rid of the lime scale, or is it called lime scale? I don't know. How does it actually work? Because that was the question that Hannah asked. And if we had quit class early, you would not have had to answer to your question, Hannah.
You got 4 minutes.
I got 3. So
You got 3.
here's what the water softener does. You have calcium carbonate, calcium and magnesium in the water. And you want to get rid of that. So what you do is you introduce sodium. The sodium will, in this case, the sodium will attach with the carbonate, detach from carbonate. You put in, and attach to, now I'm saying this wrong. I studied this beforehand to make sure I do it right. And the calcium will replace the sodiums. And so basically you're going to replace in your water sodium where you had calcium and magnesium. And you pull away the calcium magnesium. You have these little rosin things that facilitate that transfer of charge, or transfer of atoms in this case, so that you take the magnesium and calcium out of the water, and that's what the softened water is. But you do now have that sodium excess. And I won't talk about the purification of water. We'll stop here so you can.
You go 2 backslides. Oh, I need that one. And then I need the other one.